aerodynamics and flight, let me take a moment to introduce what makes our team Phoenix special. So, our team Phoenix was founded in the year 2011 and we have participated in many national and international level competitions. In 2014, 15, 16, we had participated in SA International and got first position among all the Indian teams. And in 2018, we have also participated in SA International in the regular class and we got 7th rank globally. And in 2019, we got first place in the design report. And we had also participated in the domestic level competitions such as SA India. And this year, we are also planning to participate in Shitij, which is the tech fest of IIT Kharagpur. Today's session is designed to ignite your curiosity about aerodynamics. So, guys, have you ever wondered how something as heavy as airplane stays in the air? What do you think makes it possible? So, you guys are open for the answer in the chat box. Does anyone is having any idea regarding this? So, I guess in today's workshop, you'll clear all your doubts and queries regarding aerodynamics. Next slide. So here in this image, you will see that there's an airplane and here we are having total three axes. The first one is the longitudinal, second one is the lateral, and the third one is the vertical. So the longitudinal axis, it extends from the nose of an airplane till its tail, and it is basically responsible for the rolling motion of an aircraft. And the second one is the lateral axis. It actually extends from one tip of the wing to the another, and it is basically responsible for the pitch motion of an aircraft. And the third axis is the vertical axis. It actually runs vertically through the center of the gravity, and it is basically responsible for the yaw motion of an aircraft, as you all see in the given diagram. So, guys, let me tell you one thing. It's better if you'll note down all these things because during the induction process, you're gonna get the extra edge because we're not going to tell you all these things again and again. So that's why you all should make notes and all, right? So in this diagram, you all see that this is a picture of an aircraft. So in an aircraft, we are having total three parts. Basically, the main parts are only three. This whole body, this the cylindrical body, is known as the fuselage, and these two are called as the wings, and the rear part is called as the tail. So fuselage is actually the main body of an aircraft, and basically we focus on the RC planes. So we'll place all the electronics inside our fuselage, and these two are the wings. And in wings we have further classification. They contains the parts such as flaps, ailerons, slats. You all can see here in the image, I guess. And in tails, we are also having the further classifications such as vertical stabilizer, horizontal stabilizer, rudder, and all. We're gonna discuss all these things later. Next slide. So, firstly, now I'll tell you about wings. So, the wing is the primary surface that generates the lift. Now, the question arises that how it actually generates the lift. So the reason behind is because of the certain specific shape of the wing, that is, it is having actually the airfoil shape. So the top surface of the wing is usually curved as compared to the bottom surface, and on the top surface of the wing, there's a less pressure as compared to the bottom surface. So because of the pressure difference, we'll realize that there is a force which will going to be act in the upward direction, and that force is called as the lift. But the main phenomena which is responsible for the lift generation is actually downwash. You guys might not be familiar with the term downwash, but I'll tell you. I guess you all might know what is Newton's third law of motion, right? It basically says that every action has an equal and opposite reaction. The same uh, on the same phenomena, downwash also works. So what happens? Actually, the air pushes. Actually, the wings pushes the air in the backward direction, and in the resultant we'll get that air also pushes the wing in the forward direction. So this is the main phenomena for the generation of the lift. Now we'll proceed towards a Q&A round. Next slide. So I'll be having a question for you all, and you'll all have to write your answer in the chat box. So the question is that what is the primary function of the wings on an airplane? Option A is to control the pitch, B to generate lift, C to stabilize yaw, D to reduce drag. Yeah, I guess you all are answering the right. So the correct answer is the B to generate the lift. Next slide. Now we'll proceed towards the next part, that is tail. And the tail is also called as the empennage. So the main function of the tail is to provide stability, balance, and the control in the flight. Further, it is also having its further classification. Next slide. So the first part of the tail is the horizontal stabilizer. It is located at the rear side of the flight, and it actually provides pitch stability. You guys might not be familiar with the term pitch stability. So I'll tell you, it actually focuses on nose up and down movement of the plane. And it is further equipped with the elevator, and the main function of the elevator is to control the pitch. And the pitch motion is about the lateral axis. I had already told you this in the starting of the workshop. Now, the second part is the vertical stabilizer. It is upright fin that provides the yaw stability. So its main function is to provide side to side movement to the plane, and further it is also equipped with the rudder. And the main function of the rudder is to provide yaw motion. And you all know that yaw motion is about the vertical axis. I had also told you this in the starting of the workshop. Now I would like to call Tanisha for the further explanation.
Thank you, Navya. So, myself, Tanisha, and I'm from second year mechanical. Talking about the control surfaces, first we have with us ailerons. So, ailerons are the movable surfaces on the outer trailing edge of the wings, which are used for controlling the roll motion, that is, the rotation around the axis of the fuselage. The ailerons are coupled so that when one swings up, the other swings down. As you can see in the image, which is circled by the green line, that when one aileron goes up, the other goes down, creating an imbalance in lift between the wings, which allow the aircraft to roll left or right, enabling turns. Essentially, they control the aircraft's roll movement by changing the amount of lift on each wing. Next, we have with us flaps. So the flaps are the hinged portions on the inboard part of the trailing edge of the wings. These are used to produce greater lift at low speeds and to provide increased drag on landing. This increased drag helps to reduce the speed of the airplane and to steepen the landing approach angle. Moving forward, we have winglets. So, winglets are the vertical extensions at the tips of aircraft that reduce drag and improve fuel efficiency. Now, how do they actually work? So, winglets reduce the size of the vortex where high and low pressure areas meet at the wingtip. This reduces the drag, which improves lift and allows the aircraft to rise faster. As you can see in the given slide, there is a comparison between the vortices that is produced by the aircraft and those that is produced by the eagle. Both of these are assumed to be identical. Moving forward, we have an aircraft's elevator, which is a flight control surface that controls the pitch of the aircraft, which is the movement of the aircraft's lateral axis. Elevators are usually located at the rear of the aircraft, attached to the horizontal stabilizers by the hinges. Next, we have an aircraft's rudder, which is the movable surface that controls the aircraft's yaw or rotation around its vertical axis. It's usually attached to the vertical stabilizer or fin at the rear of the aircraft. Moving forward, so here's one of the questions for you guys. Which part of the empennage helps control the pitch of an airplane? Please answer in the chat box. Okay, so the correct answer is B, that is elevator. Moving forward, now the next topic that we are going to cover up is an airfoil. So an airfoil is basically a shape that is designed to produce lift, or in other words, it's a shape which is seen in the slice of a wing. Besides the wing, propellers and the tail surfaces are also airfoils. But here you need to remember that airfoil is just the shape and not the wing itself. So it must not be confused with the wings. An airfoil has a leading edge and a trailing edge, a chord, and a camber line. The chord is an imaginary straight line connecting the leading edge with the trailing edge. The chord is used to determine the direction of the wind. The leading edge is at an equal distance from the upper and the lower surfaces of the wing. The camber is the curvature of the mean camber line. A wing that has an airfoil with a great deal of curvature in its mean camber line is said to be a highly cambered wing. Now we'll talk about the angle of attack. An airfoil with lift also has an angle of attack as shown in the figure. The relative wind is the direction of the wind at some distance from the wing. It is parallel to and opposite to the direction of motion of the wing. The velocity of the relative wind is equal to the speed of wind. In aeronautics, the geometric angle of attack is defined as the angle between the mean chord of the airfoil and the direction of the relative wind. Next, we will be differentiating between the symmetrical and asymmetrical airfoils. So, the upper and the lower surfaces of a symmetrical airfoil are mirror images of each other. Symmetrical airfoils have zero camber, and the mean camber line and chord line are the same. They produce less lift than the asymmetrical airfoils and produce no lift at zero angle of attack. Symmetric airfoils are often used in the main rotor blades of light helicopters. Here, an example of NACA 0012 airfoil is given, which is the best suitable example for defining a symmetrical airfoil. Then we have with us an asymmetrical or unsymmetrical airfoil, which have different positive and negative stall angles, and the mean camber line is above the chord line. Asymmetrical airfoils can generate lift at zero angle of attack. Here, an example of NACA 4415 airfoil is presented before you. Now, I would like to call Rajanya to continue with the further presentation.
Thank you, Tanisha. This is Rajendra Sarkar from second year Mechanical Engineering Department. I'll be discussing how the actual aerodynamics behind a flight works. So, the first question is how a lift is produced. So, we basically have two different theories regarding this. First of all, we have equal transit time theory. So, what does this theory say? Basically, as we can see in the animation, uh, as the wind approaches towards the leading edge and hits it, it gets split into two different streams and continues flowing along the upper surface and the lower one. Now, this theory takes an assumption like it assumes that the time taken by the flow that flows above the along the upper surface of the airfoil takes the same time as it takes to flow through the lower surface. So, due to this assumption, we can easily predict that, as we can see from the just a second. Okay. Uh, Sorry for inconvenience. Basically, as we can see from the diagram, the length of the curvature uh, along the upper surface is greater than that of the lower one. That means the velocity along the upper surface of the fluid flow uh, must be greater to attain the same time to reach from the leading edge to the trailing edge as compared to the flow along the lower surface. So, uh, as we can see, we have the Bernoulli equation here. So, since the velocity head in the upper surface is higher, the pressure head in the upper surface must be lower as compared to the lower surface, because we know that the sum needs to be constant. So from here, we see that the lower surface has a higher pressure that leads to a net upward force that is termed as lift, right? And so this is how the equal transit time theory explains the generation of lift. But as we'll see in the further proceedings, the theory comes out to be a failure. Um, so moving on to the next slide. Okay, so we have different reasons for the theory to fail. Like, first of all, the assumption it has taken in the very first step is that the time taken to flow from the leading edge to the trailing edge along the upper surface and along the lower surface is equal. So this assumption itself doesn't have any mathematical proof or any physical basis. Uh, so this is the first point where it got failed. That was the first assumption taken by the theory. And on the further steps, when the lift was calculated experimentally, the actual lift was found out to be much higher than the lift predicted by this theory itself. So and uh, if we further talk on it, the theory cannot explain the variation of lift along with the angle of attack. That plays a very major role in the generation of lift. Uh, and finally, when an experimental setup was performed, the theory completely was led to a failure. Moving on to the next slide. Okay, so the experimental setup was like this, that we can see here a cross section of wing. If we assume a wing cross section like this, we can see that the upper surface of the wing has a higher length, as very high length as compared to the that of the lower one. So according to the theory of equal transit time, we can predict that the pressure in the upper surface will be much greater as compared to the lower one. That will lead to a very high lift generation, right? So but when the lift was actually calculated in this particular case, there was found actually no lift. It's absolutely zero lift was produced in this that is called in this cross section. So this led the theory to a complete failure. Now the question is how the lift is actually generated then. So the generation of lift was explained by two concepts simultaneously. One is Coanda effect, and the second one is, everybody knows of it, Newton's third law of motion. So basically, what is Coanda effect? As we can see in the video in the left side. So what we see here is, as the water flows down from the tap, it gets deviated and flows along the surface of the spoon. This phenomena is Coanda effect. Basically, what happens when a fluid flows and comes in contact with a solid surface, the lowermost fluid particle that is in the just adjacent to the solid surface comes to the rest instantaneously. This condition is known as no slip condition. Uh, Same happens for a wing. Basically, when air comes to the contact of curved surface of the airfoil, the velocity of the lowermost layer gets slowed down. But as we move away from the surface of the wing, the velocity keeps increasing, As a result, the air gets bent down uh, along the surface of the wing. That means, so this phenomena is basically due to the adhesive forces between the fluid particles and the uh, solid surface. Okay, moving on to the next slide. Okay, so let's see how Newton's third law comes into play in this case. So, as we have discussed, the air particles come and flow along the wing surface due to the adhesive forces or due to the viscosity. So basically, the air. What does an airfoil do? It basically pushes the air molecules in the downward direction. That is called as downwash effect. And due to this downwash, as a reaction force, the airfoil experiences a net upward force, and this net upward force is called as lift, and this is how the lift is actually generated. And here, this is how quanta effect and Newton's third law of motion come into play to explain the generation of lift. Now, once we have defined the generation of lift, our next aim is to quantify it. So, in order to quantify the lift, we have the expression for lift, that is L equal to half rho v squared S CL, as we can see on the screen. So, let's understand the terms one by one. Here, S is basically the wing area. V is the relative velocity of the wing, right? Or in most general terms, we can say that the V is the velocity of the aircraft. Next, rho. Rho is the density of air adjacent to the wing. Next, the term L. L is the lift. Now, the question is, what is the CL? Basically, CL represents the coefficient of lift. This coefficient of lift counters all the other parameters that other than the density, velocity, and surface area. Those parameters are countered by the term CL. Majorly, CL depends upon the angle of attack. But you have to keep in mind that there are many other parameters that affect the CL, right? We will be discussing these things in the further workshops or after your inductions. So, moving onward. So, we have to define the angle of attack. As we have earlier discussed, angle of attack is basically termed as the angle made by the chord line of the wing with respect to the relative wind velocity, right? So this angle of attack that was defined earlier basically is the geometric angle of attack, but the density was the definition was further modified, and we have introduced another term called as effective angle of attack. Basically, if you think about the asymmetric airfoil, it doesn't produce zero lift in the direct. If we place the airfoil in the direction of the relative wind, it doesn't produce zero lift. It produces a significant amount of lift. So, this in order to encounter this happening, we have to change the orientation of the mean chord to a negative angle of attack, negative geometric angle of attack. So, this geometric angle of attack, the new orientation of the mean chord of the airfoil is termed as zero lift line, and the effective angle of attack is measured from this zero lift line instead of the relative velocity of wind, right? So basically, the in layman terms, the effective angle of attack refers to the angle made by the chord line with respect to the zero lift line, right? Moving onward. So, as we have discussed, the CL, coefficient of lift, depends upon the angle of attack majorly. So, as we can see from the plot in the right hand side, we can see that the CL is a linear function of angle of attack, or we can say that it is directly proportional to the angle of attack. But this proportionality holds up to a certain level, certain value of angle of attack only. This maximum value of angle of attack is called as this specific value of angle of attack is called as stall angle, or uh, the the stall angle, or the critical angle of attack, right? At the critical angle of attack, we have the maximum value of CL, as we can see from the graph. But we can see that after the value of alpha C, that is critical angle of attack, this value of CL gets reduced. More precisely, the angle of variation of coefficient of lift along with the angle of attack becomes abrupt after the critical angle of attack. So the question is why. So let's move on to this. We can see here a video where we can see the variation of CL along with the angle of attack. We can see as we are increasing the angle of attack, the downwash is increasing, hence the CL value will be increasing. Now, just focus on here. The flow is getting separated on further increase of angle of attack. So, basically what happens, please move to the previous slide. Ikansh, can you please move to the previous slide? Okay. So, move to the next one. Please show me the plot of CL versus alpha. Yes, this is it. So basically what happens at alpha greater than stall angle, the flow separation starts, and due to this flow separation, as we have seen, some vortices are formed in the near to the upper surface of the wing. As a result, the lift produced decreases, as well as the value of CL decreases, as we can see in the plot. So this phenomena is stall. Okay, moving onward. Okay, so here we can see we have two plots of CL versus alpha of two different airfoils. This plot is extracted from the software known as XFLR5. We use this in order to plot CL versus alpha graphs and many other characteristics of an airfoil, right? So now I have a question for you, that we have two plots here. One is the upper one and one is the lower one. So now the question is, which kind of airfoil does this plot represent? The upper one represents a different type of airfoil, and the lower one represents a different type. So you have to say which one is symmetric, which one is unsymmetric. Answer in the chat box. Okay. So as I can see, only one correct answer has come in this case. No. Okay, the count is very less. So the upper one, okay, you can stop. The upper one is basically unsymmetrical. See why? Uh, as we have discussed, at zero angle of attack, the unsymmetrical airfoil produces a non-zero lift. So as we can see, we have a positive y-intercept in case of the upper curve, and the lower curve is producing zero lift at the zero angle of attack. So the curve that has a positive y-intercept will be a will be an unsymmetric airfoil, and with zero y-intercept will be having a will be the symmetric airfoil. Now I have another question in this concept. You have to say which kind of angle of attack we are plotting here. Okay, I see no answers coming. Okay, after a long time, I have received another answer. Okay, basically, this is the geometric angle of attack. Because, see, we have defined the effective angle of attack in such a way that at zero effective angle of attack, value of CL will be zero, whether it is a symmetric or unsymmetric airfoil. But we have seen here a value of positive CL at zero angle of attack. That means it is not the effective angle of attack, right? So this was an interesting concept. Moving onward. Okay, so we have the Q&A corner. What is the angle between the chord line and airfoil? Chord line and the direction of airflow. Yes, it is angle of attack, or more precisely, we can say it is geometric angle of attack. Okay. In a graph showing the relationship between the lift coefficient and the angle of attack, the angle at which lift starts to decrease is called as. Okay. Okay, everyone is correct. Uh, it is the stall angle of attack or critical angle of attack. Moving onward. Okay, so that's all from my side, and I would like to call Ayush to continue further. Thank you.
Thanks, Rajanya. Good evening, everyone. Myself, Ayush Kumar from Electronics and Communication Engineering branch, and I will be discussing with you the avionics part of the aircraft. So, before discussing about avionics, first we will need to know what is aviation. So, aviation is anything with its operation, development, or the design of the aircraft. It may include any physical aspect such as a structure or propulsion or navigation. Together, when these are combined with the electronic parts, this is called the avionics. The main avionics comprises of the electronic parts such as receiver, transmitter, ESC, servo motors, and all these are powered by the battery. Now, next slide. So this is a simple flow chart donating the which represents the connection between different electronic components. So it starts with a remote controller which sends commands at a radio frequency of 2.4 GHz to the receiver. This 2.4 GHz frequency is chosen as it offers low latency. Low latency, that is, the time gap between the user's activity and the system response, is low. Now this command received by the receiver is sent to the flight controller. It processes the inputs and gives the instructions, a set of instructions which is followed by the servos, ESCs and the motor. The flight controller is also connected to outer sensors like the accelerometer, which measures the acceleration of the aircraft, or the gyroscope, which measures the angular velocity of the aircraft, sometimes barometer, or the thermometer, or the magnetometer, which is all present in the inertial measurement unit module. Then it is sometimes connected to the onboard computer through the USB. It is done for the flight controller calibration purpose or some firmware update which has to be input in the flight controller. Then it is connected to the Wi-Fi module for the wireless connection between the flight controller and the external system. Then the flight controller through the telemetry link of 915 MHz frequency is connected to the ground control station. Here 915 MHz frequency is chosen as it offers less interference as compared to 2.4 GHz. This ground control station is simply a combination of software and hardware which handles all the telemetry data such as the battery status or the GPS status, and it can be stored for the analysis in the future. Next slide. Here comes the BLDC motor. It acts as a muscle for the aircraft. It produces thrust required by the aircraft for the lift purpose. This brushless DC motor, BLDC, it has also other type, which is the brushed one. The brushless is often given edge over the brushed one as it offers less friction due to no brush. The brushed one, along with having brush, has a commutator for changing the direction of current in order to produce the magnetic field, and in the brushless one uses an electronic controller to produce a rotatory magnetic field or the time varying magnetic field for rotating the motor. Now next slide. So here is the working diagram of the brushless DC motor. In the right diagram, the inner part where rotating arrows shown, this represents the rotor part of the BLDC motor. Then the outer part represents the stator of the BLDC motor. The stator part is a stationary. Then there are the pair of windings which is shown by the red, blue and the black respectively, and then there is a symbol which is denoted H1, H2 and H3. This represents the Hall effect sensors which is connected to the rotor part of the motor, and it is kept beside the stator. It senses the magnetic field. The magnetic field, and the rotor part has a permanent magnet north-south which is represented, and with the help of the magnetic field it sends the data to the ESC which is in the decoder circuit. So with the magnetic field data, it predicts the position of the rotor, and it provides the field effect transistor which is commanded by the microcontroller of the ESC, that which switch has to be turned on in order to decide the path of the current in the three pairs of the motor windings. Now in the left diagram, the current diagram, we can see it is represented ABC. So ABC shows the three different motor windings. Here plus sign shows that the current is going inside the motor winding. Negative sign shows that the current is coming outside the motor winding. Whereas the forward slash represents that the motor winding is in neutral state or it is used in the detection of back EMF. At a time, two motor windings are active. So here we can see that the red and the blue one are active and that black one are inactive. Since this rotor is rotating in clockwise direction, so one pair of motor winding attracts it and other pair of motor winding repels it. For example, the red one, it's the north pole, so it's the south pole, so it attracts the north pole, and the blue one is the north pole, so it repels the rotor, and together its attraction and repulsion combination, it helps in rotating the motor. Now in the left downside, you can see the BLDC motor control. So this BLDC motor is connected to the electronic speed controller. We will discuss about them later. And this is works on the PWM signal, which is pulse width modulation. These are the pulse width. So if pulse width is less, then its rate of rotation is less, and if pulse width is more, then its rate of rotation is more. Next slide. So the left video, it shows the coil magnetic field. So the motor windings, the current is flow, and this due to the flow of the current, it also generates the magnetic poles. For example, if you take the front view from the face of the coil, and in that view, if the current is flowing in the clockwise direction, then that face across the south pole, and if the current is flowing in the anti-clockwise direction, then that face across the North Pole. Due to this only, attraction and repulsion combination phenomena was happening as I discussed in the previous slide. Then in the right side, there is Hall effect sensor output. So the Hall effect sensor which was connected to the rotor, it outputs a sequences in 1 0 which are analogous to the voltage high or the voltage low. One is one output is generated when it faces the north pole of the permanent magnet of the rotor, while zero is generated when it faces the south pole of the permanent magnet of the rotor. Next slide. So here I told that two offsets of the motor windings are active at a time, while one is inactive or in the neutral state. So due to the magnetic field produced by the permanent magnet of the rotor, the magnetic flux linked with the neutral coil motor winding changes, and due to that current is induced in that motor winding, and this current induction is such that it opposes the change in magnetic flux linked with it, as it is stated by the Lenz law. Now when the current is induced, there is a voltage drop occurs in that motor winding, and this drop in voltage is taken by the microcontroller, and it predicts the positions of the rotor. So it is used in the technique where Hall effect sensor is not used. So it's the sensorless technology to predict the positions of the rotor. Next slide. So here comes the electronic speed controller. So electronic speed controller works on the pulse width modulation, as I stated earlier, and it is used to control the speed of the motor or its direction. Pulse width electronic speed controller has many inbuilt components like the voltage regulator. So if there is any spike in the voltage, it negates it and regulates down to the required voltage so that the microcontroller and ESC and all the electronic components connected to it are safe. Then there is a battery eliminator circuit which negates or eliminates the need of external battery for all the components. Then there is a processor which is nothing but the same as microprocessor, and the switching which is the field effect transistor, which I will discuss in the next slide. So in the left side, there is a microcontroller which gives commands that which Q1, Q2, Q3, Q4, Q5, Q6. These are the 6 transistors or which works as a high speed switches. So the BEC, that is the battery eliminator part. Then there is the rotor position circuitry which predicts the position of the rotor, and then there is a FET drive circuitry which triggers the FET to close the circuit or open the circuit in order to allow the current in a particular winding so that rotor can rotate. Now ABC are the one end of the motor winding which is connected to the ECE through the FETs. They all are connected at a single point which is known as neutral point. Now neutral point has its own significance. It acts as a reference for measuring the phase voltage of the motor winding A, B and C. And this is a star connection. Here star connection has an edge over other connection such as delta connection, as it is less prone to the short circuit. Now in the right side, so the first motor is connected to ESC through the 3-phase bridge connection. Then the red wire is connected to the positive terminal of the battery, while the black wire is connected to the negative terminal of the battery. Then there is a set of 3 more wires. One is the yellow wire, which is a signal wire or the pulse width modulation signal wire, also known as control signal wire. Then the red one is the positive power supply and the brown one, that is negative power supply, it is used to power the Arduino. Then at the down there is a small potentiometer. So together with this potentiometer, AC is used to control the speed of the motor. Next slide. Now comes the LiPo battery. The LiPo battery is used to power all the electronic components which helps the aircraft to fly. It is the rechargeable and made up of special type of solid polymer like ethylene oxide or its derivatives, which allow the ionic conduction even in the solid state. Since it is solid, it is in compact form and has high energy density. Nowadays, modern LiPo batteries are also available in gel-like pouch, which gives it extra flexibility. So in lithium ion batteries, which is other alternative, it has a metal casing. So it is more prone to bursting out as compared to LiPo batteries, as LiPo batteries are more flexible. Also, there is less chance of leakage in the LiPo batteries as compared to lithium ion batteries due to its flexibility, and hence also the less chance of short circuit. So it is overall safer. Now there is one S symbol in the same slide. Yes. So in the battery, there is one donation which is given by S. So S donates the serial. So if there is written 3S, it represents that the three cells are connected seriously, and each of in the series, and each of the cells is equivalent to 3.7 volt. So if 3S is written, means the three cells equivalent to 3.7 volt are connected in series together forming 11.1 volt. Then there is 2200 mAh written in orange battery. So it represents the battery capacity, and when it is connected to ESC, suppose the ESC draws the current of 15 ampere. Maybe it is marked 30 ampere, but it doesn't draw the current at its full potential. So if we take the average 15 ampere, and if we divide the battery capacity by the amount of current drawn by the ESC, such as 2200 by 15,000, it will give the amount of time the flight can take. So it will be in hours, and if we multiply it by 60, it will be minutes. To get a practical insight, it's equivalent to approximately 9 minutes. Next slide. Now this is the power distribution board. After taking the power from the battery, this power needs to be distributed to all the components, which is done by the power distribution board with the help of power module. This power module also has an inbuilt voltage regulator, which avoids any fluctuation in the voltage and provide the required voltage to all the components, which is generally 5 volt or the 12 volt. This power module also sends the telemetry data, that is the battery status or the GPS location, to the ground control station so that it can be monitored and analyzed for future purpose. Now this power distribution board is made up of FR4 material, which is epoxy-based laminated interface. It is highly thermal resistive, means it has very less effect of heat, and it has copper traces engraved on it. These copper traces are often thick to avoid the effect of heat and for good conductivity. Now next slide. So there comes the servo motor. These are small yet very powerful. They are often used to control surfaces like elevator, rudder, or the ailerons. They work on pulse width modulation signal. So in the right diagram, you all can see there is a DC motor. So this DC motor rotates at high speed and has a low torque. It is connected to the gearbox, which reduces its speed down to 60 rpm and increases the torque. Then the outer shaft of this gearbox is connected to the potentiometer. So as the DC motor rotates, this potentiometer also rotates. This potentiometer is used to verify the actual position of the shaft of the servo motor. And from the potentiometer, there is three wires coming down. One is yellow, red, and black. Yellow one is the pulse width modulation signal wire, and it contains the data from the transmitter. It receives that what is the rotation or how much rotation the shaft should have, or the target rotation. So this measures the difference between the target rotation degrees and its actual position. The potentiometer also has a voltage which is known as potentiometer voltage based on its absolute positioning. Now the difference between the actual position and target position is known as error. So this error is reduced or trimmed down to zero with the help of control circuit, which uses integrated H-bridge for performing this task. Next slide. So the left side, the left figure shows the pulse width. So when the pulse width are low, then the rotation of the servos are less. As the pulse width increases, its rotation also increases. Next slide. Now comes the GPS. It is the global positioning system. They work. They rely on the satellite signals for determining the coordinates, the set of coordinates of the aircraft. It helps in determining the location of the aircraft and also the speed of the aircraft. So if we know the GPS, if we know the location through the GPS, after some time when the aircraft is moving, we will get another set of coordinates. By taking the difference of the two coordinates and the time interval, we can indirectly also get the speed of the aircraft. Next slide. Now comes the flight controller, which is the acts as a brain of the aircraft. This flight controller takes input through the receivers and many sensors, and it processes it. Then it gives back the instructions to the EAC, servos, and motor based on the received inputs of which task they all have to perform. In advanced flight controller as shown in the figure like Pixhawk, there are many features like the buzzer. It gives the alert in case of low battery or loss of signal. Then there is a safety switch button. Safety switch button in case of signal loss. So it can be used for the return home, and then there is a GPS module for the location verification. Then there is analog to digital converter. So most of the sensors are analog in nature. This is due to the thing that analog signals are continuous in nature. So it uh, it captures the data with accuracy. But for processing purpose, the signal must be transformed to digital form. That is why analog to digital converter is used. So for low voltage analog sensor, 3.3 volt analog to digital converter is used, and for high voltage analog sensor, 6.6 volt analog to digital converter are used. Then there is LED, which is used, which states the status of the flight controller, whether there is any error or not. Then there is USB, which is used to connect it to computer for firmware update or any calibration purpose. Then there is telemetry, that is providing a telemetry link to the ground control station for analyzing the telemetry data. Then there is telemetry on screen display. So in the ground control station, there is a monitor which is displaying everything, every data, telemetry data, whether it's battery status or if the camera is integrated, then camera visuals for the surveillance purpose. Then there is DSM, a spectrum DSM receiver. It receives the inputs from the spectrum DSM transmitter. Next slide. Now comes the transmitter. So any movement like the movement of the joystick or flipping a switch, these all are recorded as an input by the transmitter, and it is sent in the form of radio signals to the receiver. This transmitter works on the multiple frequencies, which is called a frequency hopping spread spectrum. This is done to avoid the interference with other transmitter and receiver frequency. This hopping pattern is recognized only by the individual transmitter and receiver as they work in synchronous and cannot be predicted by other transmitter receiver pair. Next slide. There comes the receiver. So the transmit sends the data in the form of radio signals. The transmitter has various functionality in the form of channels. Now the data, radio signals data, is interpreted by this receiver for all the sensors to understand. It gives this data back to the flight controller for processing and giving the required instructions to other electronic devices. Next slide. So this is the circuit diagram showing all the connections of the electronics used in avionics, like the camera for the navigation surveillance purpose. That's Raspberry Pi 3B plus. This is used for some advanced purpose, advanced processing, which is beyond the capability of flight controller, like image recognition. Then there is PPM encoder. It receives multiple PWM signal from the receivers and convert them to one PPM signal, that is pulse position modulation in signal. So it is done in order to simplify the processing process. Then there is a switch. Switch is used for the manual power off or on of the system. Then there is compass, which is used to know the orientation of the aircraft, GPS for location. Then there is a telemetry kit. It comprises of the two modules. One module is connected to the flight controller and the other to the ground controller station for two-way communication purpose. Next slide. So now we'll be discussing the flight dynamics, means the motion of the drones. So it has different motion, and for the stable motion, it is necessary that the two diagonal arms which has the motors rotate in that opposite direction. Means diagonally, one pair will rotate in clockwise, then other diagonal pair will rotate in and counter-clockwise direction. Next slide. So the four rotors are rotated at the ends of the cross arm. This is done for the higher payload capacity. So this ensures that the weight are distributed equally on all the motors, and it ensures that it is able to lift the higher weights. Then unlike the fixed wing aircraft, it gives it the capability of vertical takeoff in the tight space. Then there is also precise movement capability is involved in this by reducing or increasing the pairs of the rotors. We will be discussing its motion in the next slide. So this figure elaborates the clockwise and the counterclockwise of the two pairs of the diagonal motors. Next slide. Ekans, on the next slide. So this slide shows the yaw motion of the quadcopter. This is unstable motion, yaw motion. Why I say that? Because in this all the motors are rotating in the same direction. That is the if we see from the top view, it's the clockwise direction, and this is rotation is done by the rotor part of the motor. Then to the frames of the quadcopter is attached the stator part. So according to the Newton's third law, the rotor is rotating in the clockwise direction, so the force on the quadcopter will be in anti-clockwise direction. So anti-clockwise torque is generated and it spins in the anti-clockwise direction. This is yaw motion. But if we want the hover motion, means a still position without spinning, then it is not possible in this case, as there is no opposing torque and all the motors are generating torque in the same direction. So we will be discussing how the stable yaw can be achieved in the upcoming slides. Next slide. So this video illustrates that Newton third law. The stator part is attached to the body of the quadcopter, and as the rotor rotates in one direction, reaction is implanted on the stator in other direction, and in that direction only the quadcopter rotates. Next slide. So this is the stable yaw motion. As you can see, uh, that two pairs are in clockwise direction and other two pairs are in anti-clockwise direction. So if we stop the video, yeah. So if two pairs are generating the clockwise direction, and if we increase its speed, and the other two pairs which are an anti-clockwise direction, if we decrease their speed, so it will also produce the torque in one specific direction, which will cause yaw direction. But there is also the opposing torque in this case, means when we want the hover position or the still position, we can increase the speed of the motor which is rotating at lower speed in order to achieve still position. Next slide. Now this video illustrates the pitch motion of the quadcopter. So the rear motor, it rotates at a higher speed and the front rotor rotates at lower speed. So the rear portion generates more thrust as compared to the front portion. So it lifts the quadcopter in front direction or tilt it in the forward direction. This is known as the pitch motion of the quadcopter. Next slide. Now the roll motion means the sidewise motion of the aircraft. So in this, the two left motors are moving at a higher speed while the right ones are moving at a lower speed. So the left one are moving at higher speed, so it will generate more thrust and tilt the quadcopter to the right side, which will eventually leads to its roll motion. Next slide. Now from here I would like Ekant sir to continue.
So sorry for the inconvenience, guys. Actually, by mistake, some people would have joined in the another link. So now everyone is inside this link. So again, we'll give you the recap of everything. Ekansh, please move on to the first slide. Next. So here you guys see that in an aircraft we are having total three axes. This one is the longitudinal axis, second one is the lateral axis, and the third one is the vertical axis. The longitudinal axis actually it extends from nose of an aircraft till its tail, and rolling motion is actually responsible in the longitudinal axis. And the another one is the lateral axis. It extends from one tip of the wing to the another, and it is responsible for the pitch motion of an aircraft. And the third axis is the vertical axis. It runs vertically through the center of gravity of this plane, and around this axis yaw motion is possible. So there are total three types of motion: rolling motion, pitch motion, and the yaw motion. Next slide. So here you can see an image of an aircraft. Basically, aircraft has total three parts. This main part is called as the fuselage. This is a cylindrical part, and these two are called as the wings. And the rear side is called as the tail. And further, they are having its specifications, which I'll tell you later. Next slide. So here we'll study what is actually wing. So wing is the primary surface that generates the lift. Now the question arises that why it actually happens, right? So the reason is because the wing is having its certain shape, that is, it is having an airfoil structure. That is why this happens. So the top surface of the wing is usually curved as compared to the bottom surface. So in the top surface of the wing, there's a less pressure as compared to the bottom surface. So due to pressure difference, we'll realize that there's a force which will going to be act in the upward direction, and that force is called as the lift. But the main phenomena which is responsible for the lift generation is downwash. So what is downwash? So as you all are familiar with the Newton's third law of motion, right? It is that every action has an equal and opposite reaction. So the wing pushes the air in the backward direction, and in the result, the air pushes the wing in the forward direction. Next slide. Now we'll have a question for you that what is the primary function of the wing of an airplane? Some of you have already answered, I know. It is for the rest of them. So you guys can answer your question in the chat box. I'm unable to see any response. Yeah, it's correct. The correct answer is B. Its primary function is to generate the lift. Next slide. Now the another part is the tail. Tail is also known as the empennage, and the main function of the tail is to provide stability, balance, and the control in the flight. Further, we'll discuss about its other parts. Next slide. So in our tail, we'll be having the horizontal stabilizers. As you all can see, the arrow is showing the horizontal stabilizer of the plane. So it is located at the rear side of the plane, and it provides pitch stability. So basically by pitch we are referring to that it is actually responsible for the movement of nose. It moves the nose up and down, right? And it is also equipped with the elevator, and the primary function of an elevator is to control the pitch. And we all know that the pitch motion is about the lateral axis. Now we'll proceed towards the vertical stabilizer. Next slide. So the vertical stabilizer is located at the upright fin, and its function is also to provide the yaw stability, but it is also responsible for the side to side movement, and it is also equipped with the rudder, and the main function of the rudder is to control the yaw motion. And as I told you that yaw motion is around the vertical axis of an aircraft. Now I would like to call Tanisha for the further explanation.
Okay, thank you, Navya. Now we'll be continuing again with the control surfaces. So the very first control surface we're going to discuss about is ailerons. So ailerons are the movable surfaces on the outer trailing edge of the wings and which are used generally for controlling the roll motion, which is the rotation around the axis of the fuselage. The ailerons are coupled as you can see in the image so that when one swings up, the other swings down. Moving forward, next we have flaps. So flaps are the hinged portions on the inboard part of the trailing edge. These are used to produce greater lift at lower speeds and to provide increased drag on landing. This increased drag helps to reduce the speed of the airplane and to steepen the landing approach angle. Then we have winglets. So winglets are the vertical extensions as you can see in the image. These are used to reduce the size of the vortex where high and low pressure areas meet at the wingtip. This reduces the drag, which improves lift and allows the aircraft to rise faster. Next, here is an example of the comparison of the vortex produced by an eagle and that produced by an aircraft. So as you can see, the inspiration of the problems related to the vortex are generally solved by observing the vortices that are produced by an eagle. Moving forward, we have an aircraft's elevator, which is generally a flight control surface that controls the pitch of the aircraft, which is the movement of the aircraft's lateral axis. Elevators are usually located at the rear of the aircraft, attached to the horizontal stabilizer by hinges. Then we have with us rudder. An aircraft's rudder is a movable surface that controls the aircraft's yaw or rotation around its vertical axis. It's usually attached to the vertical stabilizer or fin at the rear of the aircraft. The next topic that we're going to cover is airfoil. Before that, we'll be taking up a question: which part of the empennage helps to control the pitch of an airplane? Most of you must have answered, but those who are left, kindly answer in the chat box. Okay, since I cannot see any of the responses, okay, got one. Okay, so you guys are correct. The correct answer is elevator. Okay, moving forward. So an airfoil is basically a shape that is designed to produce lift, or we can say that it is a shape that is seen in the slice of a wing. Besides the wing, propellers and the tail surfaces are also airfoils. Talking about the different parts and sections of the airfoil. So an airfoil has a leading edge and a trailing edge, a chord and a camber line. The chord is an imaginary straight line connecting the leading edge with the trailing edge and is generally used for determining the geometric angle of attack as well as the area of wing. The mean camber line is the line at an equal distance from the upper and the lower surfaces of the wing. The camber is the curvature of the mean camber line. A wing that has an airfoil with a great deal of curvature in its mean camber line is said to be a highly cambered wing. Now we'll talk about the angle of attack. So an airfoil with lift also has an angle of attack as shown in the figure. The relative wind is the direction of wind at some distance from the wing. It is parallel to and opposite to the direction of motion of the wing. The velocity of relative wind is equal to the speed of wing. In aeronautics, the geometric angle of attack is defined as the angle between the mean chord of the airfoil and the direction of the relative wind. Next, we will be differentiating between the upper and the lower surfaces, the symmetric and the asymmetric airfoil. So the upper and the lower surfaces of a symmetric airfoil are mirror images of each other. Symmetric airfoils have zero camber, and the mean camber line and chord line are the same. They produce less lift than asymmetrical airfoils and produce no lift at zero angle of attack. An example of NACA 0012 airfoil is presented before you. Moving to the asymmetrical airfoil. So asymmetrical airfoils have different positive and negative stall angles, and the mean camber line is above the chord line. Asymmetrical airfoils can generate lift at zero angle of attack. NACA 4415 airfoil is an example for this. Next, I would like to call Rajanya to continue with the further presentation.
Thank you, Tanisha. Please move to the next slide. Okay. We have seen there that there are two theories to explain the generation of lift. One was the equal transit time theory, and another one was uh, the combined effect of Coanda effect and Newton's third law of motion. So basically, equal transit time theory used the Bernoulli equation and the concept of pressure difference above the in the upper surface and the lower surface of the airfoil to explain the phenomena of lift generation, right? And we have seen that it has assumed the as the name suggests, the equal transit time. That means it has assumed that the air transits from the leading edge to the trailing edge along the upper surface and the lower surface in the equal time in the equal time that leads to a lower pressure at the upper surface and a higher pressure at the lower surface, leading to the lift generation, right? And but we have discussed that this theory got came to a failure. Uh, Moving to the next slide, please. Like these were the reasons of the failures. Like the assumption itself was wrong first. Secondly, the actual lift generation was pretty high as compared to the theoretical lift generation. And next, the angle of attack effect of angle of attack was not discussed in this theory. And most importantly, the experimental setup completely led the theory to a failure. The experimental setup was please change the slide. Okay. The experimental setup was a hypothetical cross section of the wing that looks like this, and and if we compare the upper and the lower surface of this cross section, we can see that the upper surface has a much higher length as compared to the lower one. That means upper surface will be having a very low pressure as compared to the uh, lower surface, but that will lead to a high lift generation. But practically, we have seen that this generates zero lift, right? So this theory got failed, and in the next slide we can see we have the Coanda effect and the Newton's third law of motion that combined explains the generation of lift, right? So basically, what is Coanda effect? As we can see in the video, that the water that is falling from the tap gets deviated from its original path and flows along the curved surface of the spoon uh, due to the adhesive forces, right? And this effect is called as Coanda effect. And the basic reason behind it was nothing but the adhesive forces between the fluid molecules and the solid particles. And if we move on, we can see here how Coanda effect and Newton's third law explain the generation of lift. Basically, what happens due to Coanda effect, the air is pushed down by the airfoil, uh, and the reason behind the fluid flows along the curved surface is that the Coanda effect. So, as a reaction force, since the airfoil is pushing down the air as a downward, the reaction force is being acted on the airfoil, leading to the lift generation. And this was the correct explanation for the generation of lift. And moving onward, next we have seen the formula for the lift, and it was defined as lift equal to half rho v square s cl, where s is the wing surface area or effective area of wing. The v is the velocity of wind with respect to the aircraft, and the rho is the density of air near to the aircraft, and cl is the coefficient of lift that depend upon the alpha and some other complex parameters, right? And L is the lift. Moving on. Moving on. Here we have the angle of the definition of angle of attack as we have defined it earlier. Just a sec, guys. Okay. Uh, as we have defined earlier, the angle of attack is the angle between the mean chord line and the relative velocity of the wind. And we have defined that there are two types of angle of attack. One was geometric angle of attack, another one was effective angle of attack. Geometric angle of attack was the usual angle of attack that we have discussed, and effective angle of attack is the angle between the no lift line and the mean chord line. Again, moving forward, we have the relation between the alpha and CL, right? We have a linear relationship between CL and alpha. But this is valid after up to a value of alpha that is called as stall angle or critical angle of attack. And at the alpha equal to stall angle, we have the CL equal to CL max. And when alpha is increased further, the CL decreases due to stall. And we have beautifully described the stall in the next slide. Stall is nothing but the boundary layer separation or the flow separation. In layman terms, you can understand it is the flow separation between the fluid that flows along the upper surface and the solid surface of the wing, right? As we can see here, after a certain value of alpha, the flow is getting separated from the wing surface. That leads to the reduction in lift, right? This phenomena is called as stall. Next we have two plots from the XLFR5 software. This one we have discussed that one curve is for the asymmetric airfoil, because the upper one is basically for the asymmetric airfoil, because at alpha equal to 0 we have a positive CL max, positive CL, and for the lower one we have a at alpha equal to 0 we have CL equal to 0, right? That happens for a symmetric airfoil. Next, moving onwards, we had some Q&A, like what is the angle between the chord line and direction of airflow? The answer was angle of attack, or more to be more precise, it was the geometric angle of attack, right? And next, in the graph showing the relationship between the lift coefficient and angle of attack, the angle of attack at which the lift starts to decrease is called as stall angle, as we have discussed. Moving on. Next, we had the avionics part. Ayush, you may give an overview of that.
So good evening everyone. Here I will be discussing the avionics parts of the aircrafts. So it comprises all the designing, operation, and any physical aspects such as the structure, propulsion, and when this is combined with the electronics part together, this is known as avionics. Now next slide. So this is the flowchart of the avionics. It starts with a remote controller which sends the radio signal at 2.4 MHz to the receiver. So it is a command received from the remote controller by the receiver, which is then sent to the flight controller, and it is connected to the servos, ESCs, and motors. So it instructs them for what actions they have to do according to the input received from the receiver. Then there is the other outer sensors like the accelerometer or the gyroscopes for its inputs, which measures the accelerations or the angular motion of the aircraft. Then there is onboard computer, like through the USB they are connected to the onboard computer for the calibration purpose or the firmware upgrade. Then they are connected to the Wi-Fi module for the wireless connection between the flight controller and the external system. Then there is the telemetry link from the flight controller to the ground control station at 915 megahertz for the telemetry data analysis using the firmware or the softwares like the Mission Planner or Q Cloud Connector or INAV configurator, etc. Next slide. So now comes the VLDC motors, which are acts like the muscles of the aircraft, and it generates the necessary thrust for the lift of the aircraft. They have the electronic component controller, which generates the rotating magnetic field or the time-varying magnetic field for rotating the rotor of the motor, which gradually rotates the motor. Then it has also in circuit diagram. Next slide. If we see its circuit diagram, then it has a rotator in the inner part. Then there is a stator, which is outer part. The stator is the stationary part, while the rotor is the rotating part. Then H1, H2, H3 mentioned in the diagram are the Hall effect sensors, which are connected to the rotor and kept beside the stator for detecting the magnetic field. And based on the magnetic field detection, it predicts the position of the rotor. Next slide. So this left diagram shows how the poles are generated in the current carrying coil. So if the coil is in the coil, the current is moving in the clockwise direction. It's seen from the front view. Then it donates the south pole. And if the current is moving in the anti-clockwise direction, then it donates the north pole. Then there is in the right diagram, it shows the Hall effect sensor's output. It's a sequence of 1 and 0 voltage generated. So 1 corresponds to the when it encounters the north pole from the permanent magnet of the rotor, and 0 is when it encounters the south pole from the permanent magnet of the rotor. Next slide. So this is the left diagram shows the back EMF, how the back EMF is generated. So at a time only 2 motor windings are active and one is neutral, and that neutral motor winding is used for the back EMF detection. So as the permanent magnet of the rotor rotates, the magnetic flux linked with that motor winding changes, which generates the current in that motor winding. So this current is in a direction such that it opposes the change in magnetic field as described by the Lenz's law. Now, due to the generation of current in that motor winding, there is a voltage drop in that motor winding, which is detected by the microcontroller of the ESC, and based on that, it predicts the positions of the rotor when we are going for the sensorless technique to detect the rotor position. Next slide. So now comes the electronic speed controller. They work on the pulse width modulation signal and are used to control the speed and directions of the motors. It has the voltage regulator to eliminate any voltage spike effects. Then it has battery eliminator circuit for eliminating the need of extra battery for the microcontroller of the ESCs. Then it has a processor or the microcontroller which commands the FETs or the transistors to on to circuit break and circuit com- to switch on or off based on the sequence of the currents in order to flow in the motor winding. Now, next slide. So this is the structure, the diagram of the electronic speed controller. So Q1, Q2, Q3, Q4, Q5, Q6 are the 6 switches, which are the FETs or the field effect transistors. Then the microcontroller is the brain of this ESC, which gives commands when and which switch to turn on and when to turn off. Then PEC donates the battery eliminator circuit. Rotor position circuitry is used to detect the position of the rotor of the motor, and FET drive circuitry is used to trigger the FET in order to pave the path of
Ayush,
the.
so sorry for interrupting you. Kindly intercept politely. Now I would like to call Ikansh for the further
Okay.
explanation.
everyone, myself Ekansh, and I will be taking you through our team's current field of work, how and where do we work, and one of the techniques which we use to model our aircraft. This over here is a video of a skeleton structure of the wing made by lightweight balsa wood. It is a type of wood which is used for aircrafts. It is very lightweight and supported by rigid plywoods. Uh, these vertical sections over here, as you can see, these vertical sections over here is what we call the airfoil, and it is explained by one of our presenters in the previous slides. And the length of this wing, which you are seeing, is actually made by our team, and it is called the length of the wing is known as the wingspan, and the wingspan is about 12 feet long. And uh, to be noticed that this wing is actually the part of the plane which is going to participate in SA International, which is to be held in California in 2025. This over here is the video of our team's innovation center, where these wooden structures get their identity, where we work tirelessly not only as a team but as a family. Every step taken in the field of aeromodeling is the combined decision of the team. The target of SA International is though difficult, but our team is all set to take off high in the sky. This is a laser cutter right over here, and the team uses a lot of ideas and technologies during aero modeling. One such technology is laser cutting. This is a video of laser cutting of airfoil, which was used in the wing displayed in the previous slide. Hand cutting such airfoils with cutters and hand cutting such airfoils with cutters and surgical knives is not very fruitful, as it can lead to irregularities which can cause an unstable flight. So we use precise laser cutters. We feed the drawing from applications like AutoCAD to the machine. We set different values like output power and cutting speed. The maximum power generated by these laser cutters are around 50 watt. As you can see, the current drawing which it is making is of an airfoil which was introduced to you in the previous slides. And finally, thank you and congratulations, as you have covered a considerable part of aero modeling and aerodynamics. But before moving on to the doubt session, there are quite a few announcements for upcoming events of our team. In pre-OJS, we will be having a PPT round. You have to present a PPT based on certain problem statements which will be provided by our side. This will be for if you are selected in this round, then you will get to move to the other round, which is uh, which will be an aero modeling round, and you will get a hands-on experience on how to craft an airplane. Then after pre-OJS, we will be having our team inductions. And in team inductions, those who are currently attending this meeting and have taken out their precious time, you will be definitely getting an edge because you got to learn many new things from these presentations, and you will obviously get an edge in the induction process also. After inductions, we will be having our Techno Management Fest known as OJS. The event organized by Team Phoenix in OJS is known as Touchdown the Plane, in which you will have to create an actual RC aircraft. Yes, an actual remote controlled aircraft, uh, which will be created by you and your fellow inductees, fellow batchmates. So buckle up, juniors, as the team has a lot in the bag for you. So anybody has any doubts regarding the team or the any doubts regarding from the presentation, you can freely ask. Anyone? I guess nobody has any doubt. So, yeah, please stay in the meet. Don't leave because we will be taking your attendance. And yes, that will be attendance will be counted as we will see who has attended this meet, and that will definitely benefit you during the inductions. So, this was Ekansh signing off. So we have taken the attendance. Thank you everyone for attending this presentation. I hope you got uh, got to learn something from this presentation. There was some miscommunication from our side because there were two links generated at the end. But I hope that you got a gist of this presentation. And yeah, we will see you in pre-OJS and inductions. So you can leave the meeting.